this video, we're going to find the equation of the tangent line to this curve at x equals 0, and this curve happens to be a square root function, and hopefully you see a trapped 3x plus 1 inside that square root function, so that is the telltale sign that we need to use the chain rule. And maybe you're also seeing that trapped function as a couple of transformations as well. And incidentally, when you trap a linear function inside a basic function, of course that can produce some stretches and reflections, and that's another way of recognizing, I guess, the need for the chain rule. So before we differentiate to get our, of course, our derivative so we can find the tangent slope at this point of tangency, we better rewrite our radical as always. So we'll say f of x is going to be that 3x plus 1, which is trapped. Whether you just see it as a trapped function or a two transformations, it matters not. As long as we rewrite our radical, a square root is a power of a half, and then of course this is minus 9. So now we can go ahead and differentiate. So f prime of x is going to be, let's do the outer function first. So maybe we'll use that blue color for our exponent coming down in front, and then we'll minus 1 from that 1/2, of course, to get negative a half. So I've done the first part, I've done the derivative of the outer, and remember we also have to make sure that 3x plus 1 is still trapped in the derivative of the outer, and now we can proceed to multiplying by the derivative of the inside function. Of course, we'll just produce an extra 3, but if you want to do that in an extra step or a separate step, that's completely fine. So there's our derivative of the outer with the inner 3x plus 1 trapped multiplied by the derivative of the inner function. Of course, that is our chain rule, and we should probably clean that up a little bit, at least differentiate that inner function would be a good plan before we go ahead and find our tangent equation, or at least the slope of our tangent equation. So this is going to produce a 3, and I think I'll just erase that. So I don't have to write that all out again. The derivative of 3x plus 1 is just multiply by 3. So we're going to have a 3 times a half, which of course is 3 over 2. So our derivative is going to end up like the 3 on top, a 2 on the bottom. Maybe I should color code that again so you know what I'm moving around here without erasing that. So there's our yellow 3 on the top. And of course our 2 is going to go on the bottom there. I'm not sure if the color coding is necessary, but it only takes a few extra seconds. And I think most importantly, let's move that negative power to the bottom. This is going to be 3x plus 1 to the power of a half. And of course, I think we'll just go back to writing that as a square root again. And there's our original trapped 3x plus 1. Now, incidentally, we don't have to worry about this too much in this video, or I guess not at all in this video, but if you keep in mind that, 3x plus 1 can be equal to 0. So it's a good thing this question isn't asking us for a tangent equation at this specific x value, because that would make our derivative undefined, which means our tangent slope does not exist there. And actually what we're going to have there is a vertical tangent slope, if you check it out on your GDC, which we might do as a little add-on here. So if I solve 3x plus 1 for x, of course I'd subtract 1 and I'd divide by 3. And this looks like that if we're trying to find the tangent slope at x equals negative a third, we're going to run into some issues with our derivative. So that actually means we have a tangent line that's straight up and down. And if you remember your pre-calculus training, a vertical line has a slope that's undefined. So there's a connection to make here as well with that with this function, or with any function that has a denominator quite often. It's quite likely that you can run into a vertical tangent or possibly a vertical asymptote or a break in your function. So I think we will still check out that point of tangency with our GDCs in a few more minutes, just to show you that there's something really weird going on with our function there at x equals negative a third. But more to the point here in this question, if we can find our tangent slope, which we can get, of course, by evaluating our derivative at x equals 0. This is actually fairly convenient because now we're just going to have 3 on the top and a 2 multiplied by the square root of 1. If I substitute 0 in, for x, that 3x is gone, and there's not much point in writing a square root of 1 on the bottom with that 2, so our tangent slope is just going to be 3 over 2. So we have a very convenient point of tangency there. It allowed us to do this without a calculator. So I'd be treating this as a paper 1 question for sure. Now don't forget, we also need our point of tangency. So we have a point of tangency happens at x equals 0. We also have to figure out what our y value is at that point of tangency. So I'm evaluating my original function, of course, and not my derivative anymore. So if we go up here and say, what do I get when we input 0 into this function? Well, we're going to get square root of 3 times 0 plus 1, which is root 1, minus 9. And I think you can see that this is going to be 1 minus 9, or negative 8. So our point of tangency is 0 and minus 8. So now we can go ahead and do our basically pre-calculus work. It's all that's left. We'll use our point slope form and get our equation of the tangent. Now incidentally, another thing to consider here, just if you come across this in some practice problems, if this was the equation of the normal, there's not much else to do other than make sure you take the negative reciprocal of your tangent slope. So you'd have to flip that upside down as 2/3 and negate it, and everything else would be the same. You would still use the same point of tangency. So let's get our tangent equation, and then we'll wrap up by having a quick look at our TI Inspire, our graphing calc, to look at this function and this point of tangency, and also check out that weirdness at x equals negative third that I mentioned earlier as well. So here's finally our tangent equation. So y is going to be the slope, the x minus x1. And I'm going to, instead of having that minus y1 on the left-hand side, I prefer to write it over here. It's much faster, I find, or maybe not much faster, a little bit faster. So here's our tangent slope, which is 3/2. And this, again, is a really convenient x value to have because that makes us, there's no fraction work to do. When we have to multiply 3/2 by x minus 0, it's just going to be 3/2x. And then we just tack on our minus 8 here, which, of course, is just subtraction. Instead of saying plus and negative, and then we're essentially finished. We'll have our tangent equation. It's going to be y equals 3/2x. So of course, if I expand this out, and if that number had been anything other than 0, we'd have a little bit of fraction work to do here, but of course it's 0, so we don't have to worry about that. And then just minus 8. So let's have a look at our TI Inspire and double check our tangent equation, get a look at what this function looks like, and of course check out the behavior of this function and the tangent lines at that x equals negative third, which remember made our derivative undefined. Okay, so here we are in our TI Inspire, and we'll type in our function. Of course, it's going to be the square root of 3x plus 1. And make sure that you don't accidentally put your minus 9 underneath your square root sign, right? Make sure you step out of that square root template and then go minus 9. And this is what our function looks like. So let's move this up so we can see it. And maybe get rid of that label. I'm just going to tuck it off the screen and it hides it. And I think we might turn on our grid here as well, which of course you don't need to do. So under View, which of course is in your menu button, and we can have a look at a grid. You can put the lines or the dots on, and that'll allow me to see a little bit of what's happening. And note, not to get to the weirdest point right off the bat, but we can see this function seems to start at that point, at least an x value. It's a little bit to the left, and of course that's going to be at negative 1/3. But let's put on our point of tangency, which remember was at x equals 0, and I like to do that with graph trace. Once you select that, just hit 0 and hit enter, and a second enter, paste that point right on your function and an escape, and you're ready to stick on your tangent line there with your geometry feature. So menu, geometry, number 1, points and lines, and yes, number 7, and you can click that point and you are finished. Of course, the labels get all overlap there, but there we are. There's our tangent equation, and I think you can recognize the 1.5 slope is of course 3/2, and we can see that the point of tangency is this y-intercept of this function. So one thing, since we have that tangent line in place, we can just show you that if I actually move this point down to negative 1/3, well, if it even lets me, it doesn't seem to want to even do it, so this function is quite smart, at least the calculator is. If I type in negative 1/3, what exactly is going on there? Well, you can see your tangent equation became quite strange there. It's saying 1.5 e to the power of a positive 7, I guess is what the slope looks like. So that's a pretty steep slope. So unfortunately, we're getting lots of scientific notation now in our tangent equation, but your calculator's basically saying that, you know what, the slope of this line is pretty much really, really big. And that's what an undefined slope really is. It has an infinite rise and a zero run, so it's quite strange, and you can see your calculator's definitely getting confused by it, so we can ignore that label, and we can definitely see that the reason in this case that our derivative is undefined is because at that point of tangency, we have a vertical tangent. Our tangent line is going straight up in the air. So that's, of course, a slope that we can't really define properly in math. So we say it has an undefined slope. And I got that to stick pretty close that time, but not exactly. So let's go back to the smooth sailing of the y-intercept. There's nothing weird about this tangent slope, I guess, or this tangent line. It's simply just 3 over 2x minus 8. And just keep in mind that, you know, sometimes you can get into some rather unusual situations if you have a function such as this that just kind of starts right on a point in literally the middle of nowhere here at x equals negative a third, and whatever that y value actually is. I guess we can type it in one last time, not to belabor this point. Yeah, it would be at minus 9. So that point of tangency is a no-go. Because we have a vertical tangent, and this one is, like I said, smooth sailing with the tangent equation of y equals 3 over 2x minus 8.